Tomer alla fine non viene.
I think we can start. Welcome everyone, in person and online, to week 3 of the DGI workshop New Physics from the Sky. The topic of this week is cosmic coincidences in a broad sense, including cosmic solutions to the hierarchy problems. And we start in this line with Daniele Teresi from CERN that will tell us about sliding naturalness. Please.
Okay, thank you, Filippo. Let me thank all the organizers for giving me an opportunity to speak here. I'm going to talk about this recent work that kept me and Raffaele Daniele busy for basically 1 year, last year. It's sliding naturalness. So I'm going to talk about naturalness. Hopefully, I don't need to motivate why the hierarchy problem is interesting here. But given that, recently in the community, there's been some discussion in the literature, maybe it's worth stressing that this is not, something fake. This exists and can be very concrete in situations in which the Higgs mass is calculable, is a calculable quantities. At that point, the hierarchy problem is nothing but the failure of dimensional analysis. Since Galileo, we know, and Galileo was here, since Galileo, we know how dimensional analysis can predict the natural size of a quantity as long as this is calculable. But we can say that the LHC has discovered the unnaturalness of the Higgs mass, and so the hierarchy problem is this, basically. There are a few possibilities to address it. The first one, which I call it a non-possibility, is that the LHC is going to discover something tomorrow. This is only partly, or maybe not even, a solution to the problem, because the problem exists already today if we discover new physics coupled to the Higgs tomorrow. You can try to do some complication of SUSY or compositeness that tells us why we don't have, physics now. Ideally, you would ideally you would have to have some framework in which, there's a small Higgs mass is natural, but we don't know anything like that. Some simple framework at least. Or the last option is that we have to accept that nature is unnatural, but this unnaturalness is selected dynamically. And by dynamically, I typically mean cosmologically. And I'm going to talk about this. I'm going to talk about a framework that's been developed in the last few years, so it's being developed in the last few years, which is how cosmology can select a small Higgs mass. There are many variants that I'm going to present in a moment. The general picture is that at some point early in the history of the universe, you have a symmetric sector in which you have some small scale, much smaller than the Planck mass because of some symmetry. The sector talks to the standard model landscape. So we assume that there are many vacua in the standard model, each of which have a different value, for instance, of the Higgs mass. And at late times, thanks to the symmetric sector that triggers something, some cosmological event, a small Higgs mass out of the standard model landscape is selected. There are ways of doing that. The anthropic principle is not the only way. It's maybe the most famous one, the most known one, but it's not the only possibility. And actually, in the last few years, many options have been developed. And if you read the names involved here, many of these people are in the audience. So hopefully, I do not need to motivate much this whole business. If you want to draw some distinction or to categorize these things, okay, you can have the usual anthropic selection, which means that in the standard model landscape, only a small fraction of patches have observers in it. Or you can have some kind of statistical selection, which essentially means that once some measure is defined, most of the patches will have some unnatural value of the Higgs mass, for instance. But of course, here you have to talk about a measure. Or you can have some dynamical selection, which means that after some time, the standard model landscape has this form. Only unnatural values of the Higgs mass or the cosmological constant survive. And in particular, I'm going to talk about a recent proposal in this direction, this sliding naturalness by Raffaele Daniele and myself. And let's see what it is about. So the ingredients of the game, which are essentially general throughout this, at least throughout these dynamical approaches to the hierarchy problem, is that first, you have a landscape for the Higgs mass, and this could come from string theory or it could come from field theory. This is difficult to observe. So typically you have the freedom of doing basically whatever, almost whatever you want in this sector. And then you need to have some scalars that do something in the early universe. And on general grounds, you can convince yourself that these scalars need to be light. NDI argument in our work, which I'm not gonna repeat here, but essentially the lightness of the scalars, which means the shift symmetry acting on this scale, is typically inversely proportional to the typical scale of the scalar potential, essentially to the cutoff of the theory. And then you have some way to make the scalars phi communicate with the standard model in such a way, this communication is sensitive to the Higgs wave, not to the cutoff of the theory, to the Higgs wave. And essentially, as Nima, Raffaele, and Hyundo, who's here, argued very recently, essentially you have three possibilities. You can make the scalar communicate via GG dual operator. G is the gluon field strength. Via FF dual operator, where F is some field strength in a dark sector. Or via a very special form of a 2 Higgs doublet model that is sensitive to the Higgs wave rather than the cutoff. And this typically governs the phenomenological signatures that these frameworks have. So let me discuss sliding naturalness in detail. So there is a novel way to address the hierarchy problem and solve at the same time the strong CP problem, explain dark matter, and other things that I'm going to discuss. And again, this is work by myself and Raffaele, who's one of the organizers actually of the workshop. So for all complaints, you can talk to Raffaele from next week. For all things, you can talk to me this week. So the mechanism. The idea is that we have a landscape. In the particular case of sliding naturalness, we assume that we have a landscape both for the Higgs mass up to some cutoff lambda h and the theta angle. Now let me not discuss the theta angle. I'm going to discuss it later. So please ignore the theta angle in this sketch, but I had it like this, so I don't want to change it. So just assume that there is a landscape of Higgs masses, and each of them is populated, this landscape, somehow, for instance, because of eternal inflation or some other mechanism you can figure out. Then, after a very short time, essentially at the QCD time, what's going to happen is that all patches where the Higgs wave is far from the observed value, so either is 0 or is very heavy, will crunch, will disappear. Evolution of these patches will be very quick. And so if you follow the story for sufficiently long, after some time, after a time longer than 10 to minus 5 seconds, QCD time, yeah?
What does it mean? So do you have math that go with this?
Sorry?
Do you have mathematics that go with this?
Yes.
Do you know how to populate the landscape in
Now,
first?
to populate the landscape, you typically need the eternal
So you don't
inflation.
have mathematics.
What do you mean? Usually,
Do you have a mechanism that populates the landscape without eternal inflation? Because if you have eternal inflation, you have infinities.
Yes, but this selection is after reheating. So
What does that mean?
That when all the different patches exit eternal inflation, you have reheating, you wait 10 to minus 5 seconds, you look at all the patches that have exited eternal inflation, and you see that the only surviving patches are those in which the Higgs mass is tuned to be small.
What do you mean they have exited? You cannot just exit eternal inflation and pick and choose which. There is other patches that are not exiting eternal inflation.
Yes, yeah, of course, those are not care.
So why don't you care?
Because those are in principle empty, in the sense that reheating has not occurred in those patches. So I personally do not care what happened to an empty patch in the multiverse.
So so you're imposing anthropic arguments?
This is a very mild anthropic argument in the sense that I do not care to what happens to patches which are still inflating. Also because the mechanism that I have in mind to solve the cosmological constant problem is precisely an anthropic selection according to Weinberg.
Have you shown that these are the only patches that are relevant that have, I don't know what the story is. Are you imposing anthropics or are you not imposing?
I will be deriving that. Okay,
so then you're imposing anthropics. What happens to the cosmological constant problem here?
I'm imposing that. I'm imposing that. The cosmological constant problem is solved somehow. let's say it's solved anthropically. We don't really need to specify what solves it, but let's keep it in mind that it's solved by the anthropic argument by Weinberg. At that point, I look at the patches that have exited inflation and have reheated. I wait a time of 10 to minus 5 seconds, and I see that the only patches that survive so long after reheating are those patches where the Higgs bed is small.
Sorry,
this is mathematically.
Sorry, what makes 10 to the minus 5 special?
Is the QCD time. It's going to be clear in a moment. For this
But
mechanism,
then why are you ignoring the patches that crunch? Why are you throwing them out?
Because from the point of view of an internal observer or would-be observer, these patches live very short time and cannot have a lot of entropy inside.
So then you're talking about your opposing anthropic argument.
I'm saying
because
that,
most of the vacua, let me ask you, most of the vacua in your theory do not look nothing like the standard model vacuum.
Exactly, that's the point. We don't, I mean, we're not arguing against that. We're just saying that if you want to have a universe that remotely resembles like standard model 1, this universe will have a small Higgs web. There are plenty of other patches that are crunching very fast, and the Higgs mass is very heavy. To whatever it happens in these patches is a matter, to why we don't like these patches. If you want, at the very end, is a matter of taste. You could use just the conservative argument that these patches are extremely different from the physics that we see. And this is the most conservative attitude. If you're slightly more aggressive and you like about talking about measures in the multiverse and stuff like that, you can even convince yourself that these patches are subdominant in the 4 volume of the multiverse. But I don't want to insist on this argument because this is shaky because you have infinities.
Yeah, but you already have infinities. I don't understand what you are trying to achieve. How is it what you're trying to do without any mathematics, right? Because you don't know how to populate this universe. You don't know the cosmology of the entire universe, and you don't want to argue anthropically.
I'm saying that if you look at the patches after reheating,
I don't know what that means after reheating, because they cannot set the time equals 0. You have infinite time.
Yes, but you can look at the 4, you have a space. This is eternal inflation, a conformal diagram. You have a very weird hypersurface where eternal inflation ends in the different patches. Then I wait 10 to minus 5 seconds.
Sorry, it doesn't end. Here in our patch, if you have cosmological constant of 10 to minus 33 eV, it's not ending. We have it in our future. That means it's in infinity.
But inflation, we have reheated.
So what? We spend some blip of time to be reheated, and then there's still infinity of internal inflation. So internal inflation has not ended. I don't know what you mean by that.
I mean that all patches have been, if I look at patches that have been populated in the sense of reheating for a sufficiently long amount of time.
What does long mean compared to infinity? What sets the unit of time if you have true infinities?
Any universe that is filled not by radiation or matter because of reheating, but is filled because of the Sitter radiation, for instance, will certainly look very different from ours. This is undeniable. I'm talking about, I do not care about patches that have Boltzmann brains, for instance, that have, that are populated by the Sitter radiation. I do not care about
why are you ignoring those? Because they could have universes too.
Okay, we can say that we address the hierarchy problem up to patches that look very different from our universe, for instance, because they are populated by the Sitter radiation. Okay, this is the minimal.
I'm sorry, this doesn't make any sense. Sorry.
Well, maybe we can, leave this for the discussion after both talks, or.
Okay, if we assume that it makes sense to look at those patches after reheating, what I am trying to say is that if we wait a sufficient amount of time, those patches, the surviving patches, will look like this. Only the ones with a small Higgs web will be present. All the other ones have crunched in a very short time as compared to to cosmological times. Then what happens to the other patches? Just a little bit of history. This crunching of unwanted patches first appeared in the context of the cosmological constant in this work by Bloch, Chucky, Michael Geller, and Tomer. In the context of the hierarchy problem, it first appeared in this scenario of precarious naturalness by myself and collaborators, but I'm not going to discuss this. After this, the same kind of idea for the Higgs mass was being used by this work that I think Csaba discussed last Friday, and this works by Raphael and myself that I'm discussing now. So the idea is the following. We have a potential that has this kind of structure. It has a very shallow minimum here and a very deep minimum here. The idea is that the structure of the landscape for the cosmological constant is such that around this vacuum, the cosmological constant can be tuned to 0, for instance, by Weinberg argument. And so this patch can live for cosmologically long time. Whereas patches in which the field phi is rolling towards this minimum or sits at this minimum, in those patches, the cosmological constant being smaller than the difference in energy between the two minima can never compensate this negative energy. And so these patches will crunch in a time of the order, an inverse time of the order, related to m star, the high scale of the theory. So only in the local minimum, the cosmological constant in the landscape can be tuned to 0. This is necessarily anti-de Sitter and will crunch. Then if we zoom in around the local minimum, the idea is that in absence of electroweak symmetry breaking is the green curve. So this local minimum exists. When you switch on the Higgs web, so in those patches of the universe where the Higgs web is large, because of the interaction with these scalars phi, they will induce typically a tadpole, they will induce some modification of this potential, and they will destroy this stable minimum. That means that the scalar phi, if the Higgs web is large, will start rolling down this potential. In particular, the relevant patch will crunch. So this part selects only universe where the Higgs web is much smaller than a particular, smaller than a particular value. This is a scalar phi minus. You can have two scalars. If you have a scalar phi plus, you can play the complementary game. And so the idea is that in the absence of electroweak symmetry breaking, this red curve here, the local minimum does not exist altogether. But once you switch on the Higgs web, and this is sufficiently large, you can create the local minimum. Again, in this local minimum, the cosmological constant can be tuned to 0, whereas in the deep minimum, it cannot. And so you have a patch that can survive for cosmologically long time. If you put all of this together, one scalar essentially selects a sufficiently small Higgs web. The other scalar selects a non-zero and sufficiently large Higgs web. If both of them are present in nature, you select Higgs web, a small but non-zero Higgs web. This is the essence of the mechanism. Let me write down a possible Lagrangian. This is just an example. You can do this, you can play this game in many different ways. This is maybe the simplest possible example. This is a phi-4 theory that in absence of the Higgs web is just unstable. In the plots before, I showed also some kind of global minimum, but in truth, the global minimum does not play any role here. As long as you can roll down to sufficiently negative energies, you don't care what happens. Those things will crunch. Yeah.
So why do you need two different scales? Is it for the standard hierarchy problem? Once is enough, right? I mean,
for the standard hierarchy problem, one is enough, but we are being maximalistic here. We also want to explain why the Higgs web is non-zero, not only why it's small. We want to explain, we want to bound the Higgs web both from above and both from below.
Yeah, but
it's not necessary.
But from below, you are adding a new scale and you are explaining a new scale, I guess, right?
From below, sorry?
I mean, if it is, as long as it is way from the cutoff,
yeah,
it couldn't be anything from 0 to this cutoff.
No, but you
and then you tell me
electroweak symmetric vacuum. The point is that
you want to put
I want to say, I mean, half of the vacuum, if you wish, they are in the in the broken phase, and you don't want those because there are many more usually than the tuned vacuum, right? So you want to get rid. I mean, people typically ignore this problem, but no, you cannot ignore it.
Okay.
Of course, you could use some strong anthropic argument to say that you don't want this these patches because the chemistry is different, et cetera, but we're trying to do, so the second scalar is such that in the absence of a Higgs wave, instead the local minimum is present. Again, this can be achieved by a phi-4 theory, at least locally. Then what happens to the deep minimum is a different story. And then you have to make this phi interact with the standard model. And one of the simplest possibilities, one of the three possibilities, is coupling it to GG dual, the gluon field strength. Why this means that the phi potential is sensitive to the Higgs wave? Well, because usual instanton effects that depends on the fermion masses. And since the fermion masses depend on the Higgs wave, at the very end of the day, you're going to have some cosine potential, whose size depends on the Higgs wave. And in the relevant regime, you can just approximate it by the quadratic term. You don't need to look at the whole cosine structure. It's just parametrics. Essentially, you can convince yourself that if you choose the parameters of the model correctly, from the point of view of these scalars, this quadratic term can generate a minimum if lambda is big enough. And from the point of view of these scalars, the tadpole term for phi minus dominates. So if lambda is too large, this tadpole would destroy this local minimum. And so again, you're selecting, if you do the mathematics, a size of the potential, which is a monotonic function of the Higgs wave, between these two values that you can choose conveniently.
Maybe you said before, but I didn't get why there will be minimum when you go to larger negative is negative. It cannot be small cc.
Because the assumption on the landscape is that, let me look, for instance, here. Actually, can I draw a moment? Hope that nobody hates me. I will try to explain it in Word also for people that cannot see the blackboard. So the assumption, sorry? There is a camera, okay, good. So if this is the energy split between the two minima of the potential, the assumption is that the maximal CC in the landscape, let me call it Vmax, is slightly smaller, at least slightly smaller than this delta V. It could be even much smaller, but this is sufficient. This means that as long as you have this small coincidence, which could even be explained by symmetry, that this is the energy span of the cosmological constant, and we'll be able to to set this to 0, but not this to 0. In the landscape, the energy of this global minimum is necessarily negative and sufficiently negative, typically of the order of m star to the 4th.
But do you have an explicit example where this is
yes,
the case?
the explicit example is actually not by me, but is the person in front of you, in the sense that we used to motivate it as a toy landscape, a field theory landscape by Savas, Niemann, and Kakru, in which you have this kind of structure, basically. It has to be just protected by symmetries, in particular supersymmetry in this case. And yes, you can do it. It's a famous paper by Savas, Arkaniamed, and Kakru. I mean, this is a usual property. It's independent on this story. If you want to have a landscape in field theory, you need to do something to protect the structure of the landscape that you need.
Because just to finish, because I was always in my mind that eventually you want to put also gravity and everything. So
yes.
In general, you always have also vacuum with CC of order M Planck or M string.
No, you need to have some symmetry in the landscape. In particular, the solutions that they found is that a combination between supersymmetry and R parity and R symmetry essentially protects and makes the center value of the scant vacuum energy and the variance of the scant vacuum energy of the same order.
This doesn't happen in string theory. You're saying it's
which does not happen in string theory, as far as I know.
So you must have a setup that doesn't allow you to break supersymmetry at M Planck.
Yes. Or at least in a very peculiar way. Maybe you can break it, but you need to do something.
So if I understand your symmetric sector field correctly, it's a kind of Goldstone boson where the
It
symmetry
has
is
a very
preserved.
suppressed potential, like does not have to be a
And
Goldstone
then
boson.
that potential has a height maximum and minimum. So the difference in the whole field range should be limited. And then your picture seems violating that. So I can imagine cosine phi plus or
with one
phi
cosine,
minus.
you know, with a trigonometric function, we'll never manage to get something like this because
Yeah, so
you
I think that picture is inconsistent with the quasi or Goldstone, pseudo Goldstone picture.
as if you use only trigonometric potential, is not the kind of structure that you use, that you obtain usually, which means that the source of this potential does not have to be from instantons in the UV theory. It has to be something else. But for our purposes, you can just take, you know, the field phi and coupling GG dual. The fact that you have a periodicity and non-periodicity is usual problem of axiom monodromy or this kind of models, right? You just coupling to GG dual. You don't need to introduce extra fermions or stuff like that to generate this potential. Just take it as
then GG dual is the only delta V that you can vary by varying phi plus or phi minus.
No, this structure of the potential, this does not come from GG. This is what I wrote here, for instance, and it comes from unspecified UV sector. We have some possibilities.
But something like GG dual, no?
No, not something like GG dual. Something, for instance, symmetric potential, something like that. Doesn't have to be, you know, the instantons. This instead is instantons, but this is the standard model instantons. This is the QCD instantons, this part of the potential. Again, if you worry about how the shift symmetry is realized, is the same story as in axiom monodromy, essentially. It's realized in a very peculiar way by monodromy. Okay, here, let me tell you why I advertise that this thing solves also the strong CP problem, at least this particular implementation of the mechanism. The idea is that, as I said, the standard model, the Higgs dependent potential is this one, and this is a quadratic potential which is shifted by theta. Theta is the theta angle, the QCD theta angle, which means that if you change theta, you're going to move the effect of this stabilizing term from here to a different regions where the negative quartic dominates, and this term can never beat the negative quartic. In other words, the only possibility for this term to win respect to the previous potential and generate a local minimum is that if this occurs in the vicinity of the region where the quartic is small, which essentially means if theta is small. This way, this means that this scalar can generate a minimum only if the Higgs wave is non-zero and sufficiently large, and theta is so small, much smaller than 1, that this is essentially aligned to the local maximum of the potential. Now, the time scale for the wrong universe to crunch is 1 over the mass of these scalars. You can convince yourself. This means that these scalars need to be light, and in particular phi plus needs to be light, because otherwise it would crunch before the QCD phase transition. And if you remember that this potential, the stabilizing potential, is switched on at the QCD phase transition, you want it to crunch after the QCD phase transition, or the universe would be doomed to die anyway. That's why the 10 to minus 5 seconds that I said at the beginning. Now, the point is that being so light, these two scalars are stable over cosmological times, and they can constitute a totality of dark matter in the universe. And they get relic density in a way similar to the axion misalignment mechanism, although it's slightly different. It's slightly different first because their potential changes quite abruptly at the QCD time, the QCD phase transition time, which means that they will get a kick at that time that actually dominates the relic density independently of the initial value of their the initial misalignment angle, if you want, as long, of course, as you are inside the stability region. Otherwise, you can't. This means that the relic density, as compared to the ones of a usual QCD axion, is suppressed by theta 0 square. It's a huge suppression factor. This means that you can have very light values for this mass and do not overclose the universe. In particular, if you do the phenomenological calculation, you see again that phi plus is a light scalar with lighter than 10 to minus 11 electron volt with a mass coupling on the QCD line. This would look like an axion which is unbelievably light, though, if it were a QCD axion. Phi minus behavior, and in particular, the mass coupling relation is different from the QCD axion one. It's heavier, so it's more difficult to observe. But the best prospects for phenomenology is if either of them is dark matter. If either of them is dark matter, because of this relation, because of the fact that the relic density depends on the theta angle, you see that you will have, for phi plus in particular, you're going to have a one-to-one relation between the scalar mass and the theta angle in order to reproduce the observed relic density. If you look at this plot, you see that you can have phi plus dark matter first only if phi plus is very light, as I said, is essentially in the fuzzy dark matter range almost. So fuzzy dark matter actually probes and excludes already part of the parameter space. And only if the theta angle is large. It has to be larger than 10 to minus 12. Otherwise, you cannot do the relic density, which means that you need to have positive results at future EDM experiments. If you don't have positive results at future experiments, near future experiments, or mid-future experiment, you can exclude completely this scenario. You cannot tune anything against anything. There is no which. This prediction is robust. There is nothing you can do if you don't see it. Even phi minus is not just a line, it's a region because there is an additional parameter, but the story is essentially the same. There is a strong relation between the theta angle, which means EDM experiments, and the mass of the dark matter. In principle, if you observe dark matter in this range, because of, thanks to cosmology, for instance, and you observe the theta angle because of EDM, test this smoking gun relation, and you say, okay, we are here or we are not here. Okay, more in general, this was a specific realization. You can have different potentials. I said you don't have to take this quartic potential. As I said, a potential parameterized in this way, for instance, which, however, is not a generic potential. There is some symmetry that has to stabilize the hierarchy between this minimum and this minimum. For instance, it could be supersymmetry, it could be something else. But the key point is that the hierarchy problem in the standard model is turned into a stabilizing symmetry for this structure of the potential, in which you have two widely split minima. By the way, this is what cures, for instance, for the standard model potential, Higgs potential itself, if you extrapolate it to high energy. And again, we know that there must be something that protects this structure. And then another way in which you can be more general is that by coupling phi to any of the trigger operators that Yundo is going to discuss, most likely. For instance, you can couple it to the H1, to this particular 2 Higgs doublet model that I'm not going to discuss in detail. It's a particular 2 Higgs doublet model in which at Z2 forbids the H1, H2 operators, which means that you can have this term in the potential without having, without closing the loop and generating a very large cutoff dependent tadpole. It's a trigger. It's going to be discussed later. If you do that, again, you can repeat the game. Of course, the QCD phase transition is replaced by the electroweak phase transition. You have some parameter space. Again, you can do dark matter if you wish. You can raise this M star scale as high as you want, essentially. You want to look for these things. Clearly, this is not an axion-like particle anymore. So you want to use, for instance, test of the equivalence principle, fifth force, and stuff like that. Admittedly, you're quite far from the relevant line, but I think Yundo has a similar plot, so I'm not going to discuss it. Just before concluding, let me tell in a totally unbiased way why I like this scenario. I like it because the potential seems relatively simple, at least from the infrared point of view. It's a polynomial potential. The UV does not look painful. Of course, I'm saying this now, and maybe I change my mind in 1 year if we start looking at the UV. So far, it doesn't look painful. It's compatible with standard inflation, and this is a virtue, because in this cosmological natural business, almost anything, almost nothing is compatible with standard inflation. You typically need 10 to many e-folds, 10 to 100 e-folds or whatever. You can raise the cutoff of the Higgs sector very high, for instance, even close to the Planck scale. It's not affected by the measure problem in the sense that you need eternal inflation to populate the landscape. But after you for instance, but after you populate the landscape, all the dynamics occurs in radiation domination era, in radiation domination epoch at the QCD phase transition. So in principle, it's a well-defined dynamics. It's compatible with some of the swampland conjecture, in particular the Sitter conjecture and the distance conjecture. Of course, it's not compatible with the Sitter conjecture. It's not even clear why. It has some bonuses. You get dark matter for free. You get the strong CP problem for free. You get a smoking gun pattern of phenomenology. And that's basically it. Essentially, the message I wanted to give is that the hierarchy problem is still a problem. And there are new ways of addressing these problems that you might like or might not like, but they seem new, and studying naturalness could be a good option.
So thank you very much, Daniele. Other questions or comments? Yeah, I'm the first.
Sorry, so I didn't get what the value of F is for your 10 to the minus 11 electron volts for the mass. Sounds like a huge F,
F
right?
is huge. F is huge,
like,
but not the field range. So the field traversed here can be sub-Planckian. F there is just, it measures an interaction strength. Of course, it's not compatible with the scalar with gravity conjecture, the scalar version of the gravity conjecture. But so, the field traversed by phi can be sub-Planckian. But
F is transplanckian. The value of the parameter.
To get dark matter is transplanckian, definitely. But the field does not have to move for so long. The potential has to be under control in this region. Actually, not even in this region. Has to be under control in this region, sufficient for the vacuum energy to become negative and crunch, which could be here, it could be before that. So here, the potential has to be under control, there is no doubt. And ideally, we can have it, it depends on parameter, it's smaller than Planck. F, measure the interaction strength of these scalars with gluons, has to be tiny. For instance, you can think to clockwork solutions if you don't like transplanckian F or similar business.
Thanks.
Other questions or comments? Wait.
Do you understand correctly that the dark matter part is independent of all the rest?
The dependence is that, of course, you can solve the hierarchy problem and the strong CP problem without these guys being dark matter.
But let's say I don't care about the hierarchy problem.
But still you solve the hierarchy problem.
No, let's say we don't solve the hierarchy problem. This still, the dark matter part is still the same?
No, we impose that we solve the hierarchy problem. It's in this relation. Essentially, this lambda 4 is lambda 4 QCD, which means that the size of this potential is, well, this actually is the same, sorry. I'm sorry, it's this one that is changed. So this is the same. The phi plus phenomenology is the same. It's phi minus that is affected because we imposed something in these formulas. For phi plus, we did not impose because QCD is there, so it will generate this value. So if you want, this is a novel solution to a strong CP problem. It can be decoupled to the hierarchy problem for phi plus. Phi minus is not playing a role for the strong CP, so you don't care. It's true, yeah.
Yes.
Sorry, could you repeat what you said about eternal inflation? Just now you said that it doesn't require many E-folds, but you need eternal inflation to populate the landscape.
It does not require many E-folds in the last stage of inflation. So in the cosmic inflation, the inflation that generates the primordial fluctuations. You need something to populate the landscape. If you populate the landscape by a very long period of inflation, possibly eternal, of course you need a long period of inflation at that stage. But not in the, for the cosmic inflation. So not for the ones that generate the primordial perturbations, for instance. You need something that populates the landscape. If you have a novel way to populate the landscape that does not use eternal inflation, you don't have to say the word eternal inflation anywhere in this business. I do not know any other mechanism, but could be even my ignorance.
Thanks. So I don't see other raised hands. Any question from Zoom, maybe? No. So let's thank Daniele again.